Alright, hello and welcome. This is going to be a long video. This is going to be the chapter 4.5 Crash Course in Covalent Bonding and Intermolecular Forces. Um, so what I'm going to be doing, just to give you a heads up, is I'm going to be going through this entire PowerPoint or slideshow um, just pretty thoroughly. And then I have the practice problems up, which I'm going to go through. Just kind of how to do them, or like what I'm expecting from you, I guess. I'm not going to do the whole homework. That's for you all to do. I will put up the answers. Just as a quick note, this is the honors version of the slideshow. I'm going to be experimenting, I guess, with putting in chapters so that when something that is only for the honors class comes up, you can skip it if you are in the scholars class. Also, I think having chapters will hopefully make the organization of this very long video a lot better. I'll probably put in just chapters for the different days. When there's a break for honors, that type of thing. Okay? So, without further ado, let's just kind of get into stuff. I'm going to be able to use the typing here just to kind of draw stuff out. Alright, so covalent bonding. Now, the first thing I started out with is just talking about metals and nonmetals. And all you really just need to know here is that metals are most of the periodic table. All this stuff, they are metals, and the nonmetals are these elements. And hydrogen. Hydrogen is a very important nonmetal. And then these metals and these elements in the middle here, they are metalloids, semi-metals. They're kind of a combination of the two. It's just something that I need you guys to know, just without really going into depth with it. All right. Okay. Alright, so ionic bonds, what we've been seeing is between a metal and a nonmetal. So here's sodium, right there. Here's chlorine, just even by the colors, nonmetal and a metal. And we have metal, sodium, donates this electron to the nonmetal, makes a positive ion, negative ion, and they are attracted. Okay, so this is an ionic bond. We've done a lot of these, Okay. So instead of ionic bonding, instead of donating electrons between nonmetals, we see that they are sharing their electrons. So this fluorine is taking this electron here. This fluorine is taking this electron here, and they are sharing them in a bond. So you can write it out like this, with the electrons kind of in the middle. You could draw it in as the line here, which we'll get to, and you're going to be seeing a lot of. But if you count out all the electrons here, 1, 2, 3, 4, 5, 6, 7, 8. So this fluorine now has 8 electrons, which means it is happy. It has a full octet. Full octet. That's what we like to see. Alright, so fluorine has 7 here. It's basically sharing this electron, and this fluorine is sharing this electron. And that's how we get to 8 each. So we draw this out with just a line in between it. This line is 2 electrons. 1 from each atom. So this line is what we're going to call our bond. This is our covalent bond. And it represents 2 electrons. So every line that you see between atoms is 2 electrons, 1 from each atom. And you're gonna see a lot, especially when I get to the last day, where they're not going to write in the valence electrons. Alright, you're gonna see something that looks just like this. You see this a lot with organic molecules. You'll see something where it's just like this. Just as an example. And there's an assumed that there are these valence electrons. They do exist, and they are there, but they're commonly not written. Alright? So what I'll have you do, especially in the first part, is really trying to calculate, with the valence electrons and counting them in. But as we kind of get more comfortable with this, you're going to see a lot of structures without the valence electrons, because it's just, it's not necessary all the time, especially when you've got something like, I mean, if you wanted to write out this, right, you'll just see it like this instead of 1, 2, 3, 4, this. It's just a lot less chaotic. Alright, so I want to make that point clear. And our formulas, this is again formulas. So I should just say, I should mention here, here's a formula. It tells you how many atoms there are. We call the structure. The structure is just all the atoms bonded out like this. So when you see something like this example that I just had, sorry about that, I misclicked a button. So our formula looks like this. When you see a formula that looks like this, or a structure, the formula for this thing would be, well, we'd write it differently, but it would be, you could write it like this. Or you might write it like CH4O, something like that. So this is the formula, this is the structure, okay? And we'll start caring about formulas a lot when we get to chemical reactions. For now, we're really going to stick with structures. Alright, so that was a single bond. We can have a double bond. This is two pairs of electrons. So we have so this oxygen and this oxygen form a bond. This oxygen and this oxygen are going to be forming a bond. So there's one from each oxygen. So this one is from this oxygen. This one is from this oxygen. And over here. So there's a total of 4 electrons being shared. 1, 2, 3, 4. And if you count them out here, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons around this oxygen, so it has a full octet. Here's our formula. Again, you can see it without the valence electrons. Formula is just going to be O2 because there are 2 atoms of oxygen. And we can have a triple. Okay? Same thing, but just 3 pairs of electrons. 3 from each of the nitrogens. So you can have a whole bunch of molecules that can have a triple bond. Generally, they're pretty poisonous, actually. Like, just as an example, this is cyanide. If we bond this, we can get rid of this. This is like cyanide, which is used to, it's a poison. It's, triple bonds. This is carbon monoxide, which is again poisonous. So dangerous, toxic, just really not good stuff. So triple bonds are generally kind of scary, except for nitrogen, except for N2. Alright, and just an important note, hydrogen only goes up to the 1s2, so it only needs 2 valence electrons. So I'll tell you straight up, if you see hydrogen in a covalent bond, it's just going to be like this, and then this is going to be any other element. Because this is 1, 2. So this hydrogen is going to have our 2 electrons, and it's going to be done. You will never see leftover valence electrons on a hydrogen and a bond. That is impossible. Okay? Or at least not energetically stable. If you had enough energy, you can do whatever you want. And I'll move my camera. Just some common molecules here. Okay? Just showing you, you're gonna have to count for each of these, elements, how many valence electrons there are. Can you really stop doing that? All right. All right. So, right, we'll count this water here. Here's water. This oxygen has 1, 2, 3, 4, 5, 6. This bond is 7, 8. So we can count out how many valence electrons each of these atoms has. Alright, so to do this, we have to count valence electrons into our, how many valence electrons should this molecule have. And to do so, we have to count up all of the electrons, all the valence electrons from all of the constituent atoms. So carbon has 4 valence electrons. There's 2 oxygens, each with 6. And we add this up, we get 16. And if we look at the correct structure of CO2, as I've counted out here, there are 16 electrons. Okay? And when you have an ion, so these polyatomic ions that we spend so much time on, they have an extra electron, or 2, or 3, depending on the charge. Alright, so it's always going to be a negative, except for ammonium, but we're not going to worry about that. But this is a -1 charge. So we have to add 1 more extra electron. So again, because electrons are negative, we have to add 1 extra electron. So oxygen has 6, hydrogen has 1. This is a -1 charge, so we have to add another electron. And we add 6 plus 1 plus 1, and it gives us 8. And I'll just show this. If we were going to do the sulfate ion like this, we'd count this up the same. So sulfur has 6, oxygen has 6, and there's 4 of them, so we have to multiply that by 4. Plus, from our charge, we would get this 2. So we added this all up. So SO4, the 2 minus, should have 32 valence electrons. Okay? Just showing you how to do that type of stuff. Okay? And I think I do show the sulfate just later on in this presentation, and at that point I will show you that it does have 32. Alright, and here it is. So this is the first thing that is just for the honors. So I will put a chapter in here. Is more than one structure. Alright, so if we look at this nitrite formula, you could have the double bond on this bond, or you can have a double bond with this one. Okay, so this is one of those exceptions, or one of those examples where you can have a slightly different structure depending on which nitrogen or which oxygen nitrogen bond you put the charge on. And how we just denote this is with arrows. So we put the 2 structures. If it's an ion, you put the whole thing in these brackets. So you would take these brackets, we use these for ions, put the charge outside. We don't have the time for me to be strict about this, but I'm telling you how this is kind of done. But this arrow means that both of these things are viable, possible options, and they are the same. Okay? So there are cases where you could do something like really kind of wacky that just doesn't work. Like if we take carbon dioxide, for example. That should be okay. This is not a resonance of carbon dioxide. Alright, this only really happens when the double bond could be here or it could be here. You have like this leftover kind of bond. These are not resonance forms. It's only when this double bond, or it could be a triple bond, it could be on either side and makes it work. Okay? Just want to make that clear what that is. So both of these structures work. The double bond could be over here, or it could be over here. You're not taking two double bonds and making a triple and a single bond. That is not resonance. And the way that we're going to write this is kind of like a 1.5 bond, because both of these bonds are going to be the same energy and the same length. So even though it looks like this is a double bond, this is a single bond, it's really somewhere in between. Okay? And here's just some other examples. Move out of the way. If you count here, I don't think it's best to count, but there's 6 plus 4 plus 6 plus 4 plus 2 plus 4 plus 2 plus 4. That's how many valence electrons there are in this structure. If you add this all up, you get to 32. And that's for all of these structures. So it's basically, it could be a single or it could be a double bond. And you're just moving around a double bond around. I just want you to recognize this. All right, that's all I'm going to ask for you. I'm not going to ask you to write this or kind of determine it, but just talking about it. Okay. All right. So that's all for that. So welcome back, scholars, folks. We're going to talk just briefly about some of the exceptions. The only exceptions is that boron. Where's my pen? Come on. Boron can have 6 valence electrons. Beryllium can have 4. Okay? We look at this. This boron, 1, 2, 3, 4, 5, 6. This is good to go. Beryllium can have 1, 2, 3, 4. We are good to go. Okay? It works. It's because the atoms are small. And finally, we have what is known as an expanded octet, which means that this atom can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can have 12 electrons around the sulfur. You can also have xenon. Xenon can form, which is a noble gas, it can form molecules because it's big, but this has also an expanded octet. I'm not going to throw these into you as a question, try to trick you up. I will tell you when it's an exception, but you're going to have to know, when I say exception, you're going to have to reference the slide in your notes. The last thing we have to do is naming. Alright, we can name these molecules that have just 2 elements in them. Alright, some of them have common names like water, which is over here. It's also dihydrogen monoxide, but we'll call it water, but it does have a scientific name. Alright, so what I'm going to do, I'm going to show you just how to do this with this kind of made up molecule. Alright, so this is a made up, this does not exist. I'm just making it up for the sake of doing it. Okay, so the first thing that you need to do is the first element, the one on the left. You write out just the element. So boron is B. So you write out boron. Okay, you take the number here, or subscript. Okay, that's how many boron atoms there are. So there's 3 boron atoms. We're going to take this 3. Here is our 3. We're going to use this prefix in front of the word boron. So this is going to be tri-boron. The exception is that if it is the first element and it is a 1, you do not write it. So we do not write monocarbon here. No. Alright? So carbon, there's only 1 carbon atom here. So we wouldn't, we do not take the mono. Alright? That's the other exception. So we just leave this as carbon. So instead of monocarbon, just carbon. Okay? For the second element, you're going to take the IDE ending. I think I spelled fluoride. I always spell fluoride wrong. Alright, so you take this ending, and then you're going to use, these are the IDE endings. So that's going to be fluoride, oxide, phosphide, bromide, that IDE ending, oxide, right? Oxide, this is all oxides. And then you're going to take that number again, you're going to find this, and you're going to take hepta. I kind of ran out of space here. So this molecule would be called triboron heptafluoride. Okay? I don't think this is that difficult. I'm not going to be a stickler. You don't need a double O. It's not monooxide, it's monoxide. If you wrote monooxide, I'm not going to take off. I'm not trying to be harsh on grammar. Alright, but that's basically how you're going to name these things. You take these numbers, I will give you these prefixes on the Quiz Plus. I'm not going to make you memorize this. But that's basically it. Okay? Let's go. So here's our recap of day 1. Alright, here's another chapter, another marker is going to be done. Let's go on to day 2. Okay? So again, we have metals and nonmetals. This is just some of the properties of metals and nonmetals. I don't need you to know this like too much. This is really just, I'll ask you a question on it. If you copy this chart, you should be able to do it. You're just gonna have to tell me which element is a metal, which is a not. So if I say on your homework oxygen or iron, which one is a metal, which one is not a metal, and then which one of these will be higher or lower depending on what it is. I'm not trying to make that difficult. Okay, metals, they can bond by having their electrons kind of float all the way around. The term is delocalized, which means that electrons are not bound to a certain atom. They're just kind of free to roam all the way throughout all of the other metal atoms. All right, just having this here, just want you to know this. I know it's kind of random and sticks out, but I need to just have you all know this. All right. Um, and I'm gonna skip that just to really get into electronegativity. This chart is kind of bad because I got it from Shutterstock and it doesn't give you the best values. So I'll give you the values. The values that I give you are not going to be very different from this image, and it's going to be the same effect. Okay. So electronegativity is the ability for an atom to attract electrons in a bond. The higher it is, the more electron it's going to steal. Okay? So when you have a bond between two atoms, if you have something that's, say, 3.0, something that's 2.0, we're going to say, I want more electrons. Alright, the higher negativity means the more the electrons are going to be towards this 3.0. Okay? So fluorine over here is the most electronegative. So the highest electronegativities are going to be up in this right corner, and the lowest is going to be down here. Okay? And we can think of this kind of like tug of war. To calculate, and I'm going to go back. To calculate the difference, to calculate the polarity or electronegativity difference of a bond, you just subtract the two values and you take the absolute value of it. That's literally it. Let's just say you were doing beryllium and oxygen like this. Okay? All you'd have to do is you would take beryllium, 1.6, you take oxygen, minus 3.5, And whatever value you get, you're going to make it positive. Okay? So 1.6 minus 3.5, this is going to be 1.9. And that's just how you're going to get it. It will be negative, but you take the absolute value. So the polarity of this bond would say is 1.9. That's all you got to do is just subtract the values between the two numbers. Alright, so when you have electronegativities that are the same, so any kind of diatomic molecule like ClCl, fluorine, fluorine, nitrogen and nitrogen, the electron's going to be smack in the middle because they have the same electronegativities. So this would be the perfect sharing of electrons. Those electrons will be completely shared. So both of the atoms will get equal access to the electron. In an ionic bond, you have a very, very strong electronegative atom and a very non-electronegative atom, which is sodium. So this is like a super buff guy who's going to steal this electron from a baby. Okay? And because he steals this electron, he is going to become negatively charged. Because this baby lost an electron, it's going to be positive charge, and there's an attraction force from the charges. Okay. When we have somewhere in the middle, so here's our oxygen. Where's my pen? Here is our oxygen. This guy is our hydrogen. So they are kind of winning. They're not fully won. This electron is about, let's just say it's like 70-30. So 70% of the time, this electron is going to be around the O. 30% it's going to be around the hydrogen. Okay? So they are still sharing this electron, but it is just not a fair share. The oxygen gets the electron more often than the hydrogen. And just, we call this very keyword polar. So when we talk about the polarity of a bond, we are asking us, is this bond polar or is it not polar? And the electronegativity difference, like, it's a rough guide. I'm not going to challenge you. I'm not going to make it too difficult. Because there is this kind of better... There is this better way of showing this information where it's more of a spectrum, but this is a good estimate, okay? And all you got to do is just calculate the difference. So 0.4, we're going to say this is nonpolar. Carbon and oxygen, we have a 1.0, so that's going to be polar. And sodium chloride, 2.1, is going to be an ionic bond. Okay, so if we go back to when I talked about beryllium and oxygen, and we said it was a 1.9, that's most likely going to be an ionic bond, but it's going to be very close. It's going to be either a very, very, very polar covalent bond or a very kind of weak ionic bond. All right, so it's a spectrum. Okay, so this is the term called a dipole. It's kind of hidden here. There we go. So a dipole, because this electronegative atom here, it has a higher electronegativity, which means that the electrons are more attracted to the chlorine. So this is a 30% and a 70%. So if the chlorine has those electrons 70% of the time, it's going to be slightly negative because this electron came from hydrogen. So it's kind of stealing hydrogen's electron. A little bit. Partially. I keep using those words to be like, this is not a full charge. It is a partial charge. we use this Greek symbol, delta, which you'll see my deltas get progressively worse and worse as I draw with this mouse. Um, you'll start seeing stuff that's really far off, but that's okay. Alright, so this indicates that it is a partial charge. And just to have you remember this, I've said this pretty explicitly in class, that the atom with the higher electronegativity will be partially negative. The atom with the lower electronegativity will be partially positive. So chlorine is 3.1 and it is partially negative. Hydrogen is 2.1, it is partially positive. And a molecule, if it has polar bonds, it's going to become polar. So we consider water to be very polar because this hydrogen has 2.2 and a 3.4. So we can see my numbers were a little bit off. So that's a difference of 1.22, which is going to be polar. Okay? So the only exception that I'm going to have you guys think about is when they're in a complete straight line like this. Because they basically are fighting over this carbon and it's not really, nobody is winning. The electrons kind of are being torn apart. They're kind of being ripped in half. So even though this is a polar bond, these bonds are polar, but they cancel each other out when they're in a line. And you can think of it like a tug of war. So the bonds are polar, but the molecule itself is not polar. Okay? Alright, intermolecular forces. These are definitions if you want to look at it. You can pause. This is just some background for the word. Alright, so this is another, just for honors, is something called a London dispersion force. And basically, every single atom can have this force. Every molecule can have this force. And how it works is if you have an atom, you could randomly have the majority of the electrons on one side of the atom. Okay, that can just randomly happen. So you can have a negative charge because there's more electrons on one side on one part of the atom, and a positive charge because there's less electrons than normal on the other side. Alright? And if you have two atoms that are doing this at the same time, they can form a bond. This is because it's a very random time for this electrons to be on the same time, these are the weakest, very, very weak forces. Okay? And there is a trend, the bigger the molecule. So when I say bigger, I really should have said mass. The higher the mass, and /or, if there are more atoms, the greater this force. So if you have just 2 carbons connected versus 4 carbons connected, there is more of these LDFs. LDF standing for London Dispersion Force. Alright? Alright, so welcome back for scholars. This is known as the ion dipole. This is why salt can dissolve in water, because water is polar. So this oxygen has a slight negative charge, and it is attracted to a positive ion. The same thing works over here. Hydrogen is slightly positive, so it is attracted to the negative chlorine. And to say the greater the charge, the greater the bond. This just kind of goes with what we've kind of, it's congruent, is that bigger charges, they attract each other more. Alright, dipole-dipole forces. So this chlorine here, is partially negative, this hydrogen is partially positive, and they will attract because opposite charges attract. I think this one's kind of simple, but this is two polar molecules, okay, that are connecting, they are attracting because of their polarity, because of these partial charges. Again, the greater the polarity, the stronger the bond between them. If you had, let's just say, a carbon and an oxygen where the difference is about 1.0 versus a hydrogen and an oxygen where the average is going to be like 1.5 or so, this is going to be a stronger attraction, a stronger bond. And we see that because of hydrogen bonds. Hydrogen bonds are the strongest, or stronger than other dipole-dipoles, because oxygen is so electronegative and hydrogen is so not. So it's just the attraction between the partial negative of an oxygen and the partial positive of a hydrogen. So the requirements for a hydrogen bond are: you must have a hydrogen that has a slight positive charge, and you must have either an oxygen with a slight negative, a fluorine with a slight negative, or a nitrogen with slight negative. So you're not going to see this. You're not going to see that, because it has to have that partial positive, which there is not in just H2 or O2. Alright, and just quickly, hydrogen bonding is very important in the body when we talk about proteins and DNA. And just about the strength, ion dipole is a lot stronger than dipole-dipole, and we'll see the effects of this tomorrow, actually, at the end for the honors class. But London dispersion forces are very, very weak, and it's kind of hard to notice, but this scale is logarithmic, so that's, the scale doesn't do this fully justice. Dipole-dipoles are like 3 to about 14, whereas ion dipoles over here are about, on the low end, we'll say about like 15 all the way up to 90. So there's a big range because our scale is changing, right? So these ion dipoles are much stronger than the dipole-dipoles. Here's your day 2 summary. You can look whenever. Alright, last day. The first thing we need to talk about is water's adhesion. So water, it gets things wet. Like your hair, if you go outside when you shower, it's still wet. A piece of paper is wet when you put water on it, because water is sticky because of its polarity. This negative charge, if we take glass, which is polar, alright, this is polar, you read the note there, okay? This is positive, this is negative, so they attract. So this water is kind of sticking to the glass surface. That's why if you take a glass cup and you pour it out, there's still going to be water that sticks to the glass. It's because of this adhesion. Water can also have cohesion. So co, that prefix means together. So it is water molecules sticking to itself. So here's one water molecule, here's the other. We have our hydrogen bond between the oxygen and the hydrogen. Alright, and there is a whole mathematical surface area reason for why it forms droplets. But water will form droplets because it can stick to itself because of these hydrogen bonds. Okay, so boiling points. My thing over. Alright, intermolecular forces can tell us how much energy it takes to make something a gas. Alright, and the reason why is if you have intermolecular forces between atoms in a liquid, you have to spend extra energy to break those bonds. So it takes energy to break a bond. So to break up these temporary smaller bonds takes extra energy. Which is why, in general, the more intermolecular bonds and the stronger they are, the higher the boiling point. Just because temperature is all about how fast these atoms are moving, how much energy they have. So when you increase the temperature enough, it becomes a gas. You don't have to really worry about it having intermolecular forces with another atom. Alright, so this is again for honors, just London dispersion forces, just how this works with boiling point. Alright, fluorine, chlorine, bromine, and iodine. Okay, fluorine is the smallest. So if we draw this out, this is the definition of a nonpolar bond. It's the most nonpolar bond. But it is the smallest, so it has the least amount of London dispersion forces. And because you have less forces to break up, it takes less energy, therefore less temperature to boil F2. By the time we get to I2, because I is so much larger than fluorine, we start to become a solid. Bromine over here is a liquid. Okay? The other trend is as you get bigger. If you go from this to this, it takes more energy to break up the bonds of this one. Okay? Alright, so when it comes to temperature, just adding a single polar bond, and I'll have you calculate the difference here, which is about just 1.0, but just one bond that is polar, and it takes a lot more energy in order to boil it, because this carbon is slightly positive, this oxygen is slightly negative because oxygen is a higher electronegativity, and you could have another oxygen that's going to then make this bond that has to be broken in order to boil it, because gas atoms are free. Okay, so just adding one oxygen changes the boiling point from this, I'm not saying the number, to this. And hydrogen bonding is super strong. So if we were to continue the trend, right? So as we get bigger and bigger, the boiling point goes up. We've talked about that. You would expect H2O to be around here, based off of this line. This is what you would expect. And it works pretty well down here with CH4. But we actually see this massive, massive jump. And the reason is because of hydrogen bonding. It's always hydrogen bonding. CH4 can only London dispersion force, and because it's smaller, it has a lot less of those, which is why it decreases significantly the boiling point. There's the last thing we're going to talk about is solubility, and this big thing here, like dissolves like. So something that is polar will mix well with something else that is polar. Something that is non-polar will mix well with something that is non-polar. Okay? So this is the same two molecules we saw before. Just adding one polar bond changes the solubility a lot. Over 1,500 times. Go on. Let's go to the next page. Alright, so this is why water droplets will form nonpolar surfaces, because they want to minimize how much contact they come in with a nonpolar surface. So just as a quick aside, the term hydrophobic. It basically means water fearing, like a phobia. And it just means that there's a nonpolar thing. Something is nonpolar. So this could just be all carbons, this surface, right? Whereas this non-hydrophobic could have carbons and oxygens, like that, okay? So it's better for the water to form up and stick with cohesion rather than try to bond with a hydrophobic surface. Over here, the adhesion wins. If there's positives and negatives and there's attractions over here. Alright? One of the classic examples, which I'm going to do in class, is oil and water. They will separate. Okay? So, big idea here is even though these bonds that I'm circling in this big molecule, even though these are polar, the rest of this thing is super not polar. So these bonds are a little bit polar, but this is a super not polar, which makes the entire thing not polar. Alright? Because even though these are polar, they're not that strong. Especially to overcome all of this non-polar junk. Alright? And the last thing for my honors class, I just want to talk about soap. The difference, this goes off of what I literally just was talking about, is that even though this is not really soluble in water, and that's just because these kind of, it's so little of a slight positive and a slight negative compared to the entire rest of this molecule. But when you have this charge, when you make this a charge, the ion dipole is much stronger than a dipole-dipole. Okay? And what we see here is what happens when we have a soap is this part is able to be very soluble in water because it is a negative. And this one, you'll see it's attracted to the water. It loves water, it's hydrophilic. But the nonpolar parts, they will stick together on the inside. And they will attack things like oil by bonding to this oil. So like dissolves like. So this nonpolar section is going to fit in very well with the nonpolar oil. Alright? So that's the last bit of the slides. I actually don't think we're too long right now. I just want to quickly, and I mean this quickly, go over what I'm expecting for the homework. Alright? So when you have something like the first one, you're just going to count how many each electrons or each atom has. So this boron here has 1, 2, 3, 4, 5, 6. So you write in 6 here. This fluorine has 1, 2, 3, 4, 5, 6, 7, 8. Because these bonds count as 2. Alright, so you're just going to be doing something like this. Alright, down here, how many valence electrons should there be in each molecule or ion? I'll take O3 just as an example. Each oxygen has 6. So we should have 18. Alright. When there's a charge like that, you have to add the charge as well. So if this was, let's just say O3 with a 3 minus charge like this, you would have to add another 3. Alright? Draw 2 other resonance structures. You can do this, but just note, resonance means you're changing up where those double bonds are. Alright? And then naming the molecules, I gave you examples for this. Alright. Thank you, G-Force. I gave you examples of this. Shouldn't be too bad. We go to day 2. Okay. question 1, this is just metals. That's from that graph. Question 2 here, you take the number. So here's carbon. What do they have? 2.55 minus 2.2. And you would just get 0.35. And that's all you would put for this one. Alright, and then you have to tell me, is this ionic, nonpolar covalent, or polar covalent? So 0.35 is less than 0.4, so this is going to be a nonpolar. Alright, we go down here to indicate which atoms will be positive and negative. Alright, we look at our electronegativities. Fluorine is almost 4, hydrogen is 2.1. The more electronegative gets the negative sign. The less electronegative gets the positive sign. Okay? So chlorine has 3.0, 3.1. Carbon has 2.5. So this gives us 0.6. So still polar. It's a weak polar bond, but it is still polar. And the chlorine has the higher one, so it will get the negative. The carbon gets the positive. Alright, last one, which will have more London dispersion forces. I think this is not too bad. When I say drawing these bonds, okay, you're going to do something like what I had done. Where is it? Something like this. You're going to have to draw a sketch of some kind of ion like this being held together by ion dipoles. Alright? Same with the hydrogen bonding. You're going to have to show me how it hydrogen bonds. Alright? And finally, for our day 3, just for the homework, this, why is a gas room temperature? I did kind of an example with this. Which bottle would water have a strong adhesion to? Alright, big thing with adhesion is it has to be polar. Okay? Or else it's not going to stick. So you have to determine which one of these is polar and why. Alright, so question 3 is just for honors. You have to just tell me which the increase of boiling point. This is not a trick question. There's no other forces. It's just what I'm giving you, okay? Question 4, I'm going to explain this trend. Why this bonding happens. Why is methane? Why is it a gas at room temperature, whereas methanol is not? Alright, and the last question I'm going to have you all do is just whether or not this would or would not dissolve in water. So you got to determine, is it polar or is it not polar? Alright, so that's all for this. I just gave you some guidelines for the homework. I'll post the answers on it Tuesday night. Or probably we're going to go over on Wednesday, so I'll post them on Wednesday. Okay? So that's all for me. Have a wonderful night.